Good evening. This is Physics 2212, Lab 3, Circuits Lab. Introduction. So the purpose of this lab is to use the principles of energy conservation and current conservation to predict the behavior of circuits and measure values of conventional current and potential difference. There are three main physics principles used during this lab. Ohm's law, which is V equals IR, where the electric current is proportional to voltage and inversely proportional to resistance. Kirchhoff's voltage law, also known as the loop rule, where the sum of potential differences around a closed loop circuit is equal to 0. And then Kirchhoff's current law, which is also known as the node rule, where the total current entering a node in a circuit is equal to the total current leaving that node or junction. Preview of results. A brief preview of results in this lab shows that the circuit was complete and all values were collected. And in this lab, the system was the circuit itself, and the surroundings was everything around it, like the environment, the table, the classroom, etc. So the circuit on the right in that picture, that is what we've created initially. And the initial data is the voltage is 1.5 volts, but we have two batteries, so it's 3 volts. One 47 ohm resistor, one 100 ohm resistor, so that's 147 ohms total in resistance. And then we predicted the current and the ammeters, and using Ohm's law, we predicted it to be 0.02 amps. This lab consists of two parts. First part was constructing a circuit with two 1.5 volt batteries, 2 resistors, and 2 ammeters, as I explained on the last page. And then the second part is constructing an RC circuit with a 10 ohm light bulb, 20 ohm light bulb, again 2 1.5 volt batteries, and then a capacitor. Okay, so charge and energy conservation in series circuits. The ammeter prediction was 0.02 amps. The actual measurement was 0.0198 amps, so very close. Then we reversed one of the ammeters, and it read to be 0.005 amps, so a little bit smaller. And then we replaced one of the ammeters with a voltmeter, and the voltmeter read negative 1.4 amps, and the ammeter read negative 1.5 amps, so it dropped drastically. The potential difference across each circuit was then calculated. So as you can see, from between the two batteries, we have a 3 volt increase in potential difference. Then between sections C and B, 0 volts. Then you hit the first resistor, 47 ohms, and you get a negative 0.94 volts difference. Then E to D, nothing happens. Then F to E or E to F, you hit a bigger resistor, so it's negative 2.02 volts. Then the rest of the circuit, nothing happens. Back to A, so it's all 0 volts. So the sum of the potential difference, my prediction was 0 volts, and the actual was 0.04 volts. In real life, this should be, or theoretically, it should be 0 volts, but as you can, in real life, we're not always super accurate, but we were pretty close. So this is the potential difference approximate graph that I created. The first bit in red was already done for me, and then the rest of it I created. As you can see, when it hits the resistors, it hits a steady decline, and then it flattens at 0, and then it starts the circuit again. So next we took one of the ammeters, turned it into a voltmeter, and created a parallel circuit out of it. So regularly in a series circuit, the voltmeter read negative 1.4 amps, but when it was parallel with the 100 ohm resistor, it read 0.04 amps. In parallel circuits, resistance decreases and current increases. Then we had to calculate resistance values. So 47 ohms was 47 ohms, 100 ohms, 100 ohms. Then the resistance of wire was 0 ohms, and the resistance of the ammeter or voltmeter was 0 ohms. So now moving on to the RC circuit. As you see image on the right, we were able to get the light bulb to light up. So when the battery was attached to the light bulb was on. Then when we took off the battery and only used the capacitor that was charged, the light bulb lit up, but it dimmed over time. And it dimmed much faster with the 20 ohm light bulb than the 10 ohm light bulb. And then finally we timed it, and the time to discharge the capacitor was 0.005 seconds. So very fast. Additional questions. What if I charged a capacitor with no resistor in the circuit, then the capacitor would charge immediately? Realistically, this is not possible, as there is resistance in every component of the circuit. So it would take a time greater than instantaneous to charge the capacitor. Errors, faulty equipment. Our group had several equipment issues during the lab. This may have resulted in some minor errors, but nothing major. User error. I never like to mention user error, but as it was the first time for most of us with using circuits of this magnitude, there is the possibility of user error in construction of circuits and the usage of ammeters. Thank you.